Bismillahirrahmanirrahim. Today we are going to learn basic induction motor concept. In this video we will study the development of induced torque in an induction motor, concept of rotor slips, electrical frequency on the rotor. From the very beginning, when a three-phase set of voltage has been applied to the stator, a three-phase set of stator current is flowing. These currents produce a magnetic field Bs. This is the stator magnetic field, which is rotating in a counterclockwise direction. It is saying that this is the stator winding on which cursor is flowing. When we applying a three-phase set of voltage, a three-phase set of current, this is the A, this is B, this is C, for example, a three-phase set of current flowing through this winding, and because of these currents there is a magnetic field, and this magnetic field is rotating in counterclockwise direction. Why magnetic field is rotating, we will study it like that. For example, as this is a three-phase connections, first peak is here at A, then B, then C, then A, then B, then C. So as voltage peak occurs step by step, so the magnetic field peaks occur step by step, and it looks like that it is rotatory in motion. So magnetic field is rotatory, same like I think you saw lights which turns off and on in a sequence direction. So it looks like that the lights are moving in the functions of welding or etc. Now three-phase induction motor, I will show you a simple video which will clear more concepts regarding this. Now as we study that the magnetic field is rotatory in motion, so this speed of the magnetic field is given by n is equal to 120 is the constant number, Fe is the system frequency divided by poles made by stator winding. So that's how we can calculate the synchronous speed of magnetic field. This video will clear more things. Yes. Then the rotating magnetic field, which is the Bs, passes over the rotor bars and induces a voltage in them. This is now the induction takes place. We studied that this is the magnetic field is rotatory in motion. When magnetic field cuts the rotor winding which is placed here, a voltage is induced in the rotor winding, then a current is produced in the rotor winding, and we already studied and I told you when there is magnetic field and current, by the right hand rule we can check the direction of the force. A force is act in the counterclockwise direction and the rotor starts moving.
Three-phase supply is given to the motor. The resulting current generates a magnetic flux pi. Due to the switching sequence of three-phase current in RYB, the generated
This is the sequence. It looks like that magnetic field rotates.
flux rotates around the rotor conductor. According to the Faraday law, which states that an EMF induced in any closed circuit due to the rate of change of magnetic flux through the circuit. EMF is induced in the copper bar, and due to this,
So till now we studied that according to the Faraday's law, EMF is induced, and in chapter 1 we already studied that this E induced is equal to V cross B dot L, where V is the relative motion, relative velocity between rotor bar and synchronous speed of stator magnetic field, and B is the magnetic flux density vector, and L is the length of the conductor in the magnetic field. Because of induction, the rotor current flow in the rotor winding, and this current produces a rotor magnetic field BR. And now we have two magnetic fields. One is the rotor magnetic field and other is the stator magnetic field. So the induced torque in the machine is given by this. Torque induced is equal to K is the constant multiplied by rotor magnetic field cross stator magnetic field. This is equation derived in chapter 4. We will study later, but in here we can study that how these magnetic fields are produced. This is produced by induction, and this is when we apply three-phase AC supply voltage. So the torque induced is in counterclockwise direction. In which direction force is acted, torque is induced in the same direction.
that is relative velocity.
I am showing the little videos to show you all these windings, magnetic field, and all these principles visually, so a student can understand better by seeing all these things. That's why I am adding a small portion of the video in these slides.
Thus, rotating the rotor of induction motor. Therefore, in this process, poles are induced on the surface of the rotor, and these poles always try to catch opposite poles which are rotating on the stator periphery.
So let's move on. We will discuss this in the next slide. Now we are going to study the very important concept, which is that the induction motor rotor will not achieve the synchronous speed of the magnetic field. Why? If we were in physical mode, then I will ask this from you, but now here I will tell you that why induction motor were not moving with the synchronous speed. This is the conceptual here. You have to understand that if induction motor rotor were turning at synchronous speed, then we study that V is the relative velocity between rotor bar and synchronous magnetic field speed. So when rotor bar moves with the magnetic field speed velocity, so this relative velocity will become 0. When relative velocity will become 0, E induced is V cross B dot L. This becomes 0. Then E induced is 0. There is no induction. When there is no induction, current of rotor is 0. When current of rotor is 0, there will be no rotor magnetic field. When there is no rotor magnetic field, torque induced is equal to K into B or cross BS, and this is 0. So torque induced is 0. So torque induced is 0. The rotor will now try to stop, and it will left behind the speed of the synchronous magnetic field, which is the BS. So when rotor becomes its speed becomes less than BS, then the relative velocity produced becomes greater than 0. When it becomes greater than 0, E induced becomes greater than 0. This becomes greater than 0. This becomes greater than 0, and then torque also induced, and it will act. It will try to rotor to achieve the synchronous speed. So in this whole process, rotor will try to achieve the synchronous speed of the magnetic field, but at the end it will not achieve the synchronous speed. Its speed is little bit less than the synchronous speed of the magnetic field. So that's why the induction motor rotor were not moving with the synchronous speed. This is the reason. Now here it becomes the concept of rotor slip, that rotor will not achieve the speed of the synchronous speed, which is the magnetic field, stator magnetic field speed. So then concept rise of the slip speed and slip, which is the slip speed. Slip speed is defined as simple difference between the synchronous speed and the rotor speed, which is given as n slip is equal to, already written in the slides, is equal to n synchronous minus rotor speed. And then the another term related to this is simple slip. Slip is the relative speed expressed on a per unit or a percentage basis, and its formula is like that. S is equal to n slip divided by n synchronous, and n slip is this, so S will become n synchronous minus nm divided by n synchronous. So this is the slip, and if you calculate in percentage, then it will become like that. One thing here, it is showing that if the rotor turns at synchronous speed, then slip is equal to 0. Its synchronous speed, then nm will become n synchronous, slip is equal to 0, so slip is equal to 0. And if the rotor is stationary at 0, nm is equal to 0, then slip is equal to 1. Here you can check. If nm is equal to 0, then n synchronous divided by n synchronous is equal to slip is equal to 1. It is possible to express the mechanical speed of the rotor shaft in terms of synchronous speed and slip, which is by calculating these two. I will show here how these will come. n slip is equal to n synchronous minus nm, and slip is equal to n slip divided by n synchronous. From here, n slip is equal to s of n synchronous. This will go here, it will become like that, and putting this value in this equation, which is n s n synchronous is equal to n synchronous minus nm, and here nm is equal to n synchronous minus s n synchronous. Taking n synchronous common, it is equal to n synchronous. This is that equation, n synchronous. That's how it is driven, which I show here. Now the third part which we have to study in this lecture is the electrical frequency induced on the rotor. Let's say if the rotor of a motor is locked so that it cannot move, then the rotor will have the same frequency as the stator. So if the rotor of a motor is locked, so it behaves same as transformer. In the transformer, the stator frequency is the same as the other winding, secondary winding. So this at this stage it will behave as a transformer. But if the rotor turns at synchronous speed, the frequency on the rotor will be 0. Because rotor is moving with the synchronous speed, there is no difference, then the frequency of the rotor will be 0. Here it is explaining like that: at nm is equal to 0, the rotor frequency is equal to the supplied frequency, and the slip is equal to 1. At nm, n is equal to n synchronous, the rotor frequency is equal to 0 and the slip is equal to 0. And slip is equal to 1 and 0, we already checked it from in previous slides from the formulas. From the when nm is equal to 0, fr is equal to fe, at this stage s is equal to 1, and when fr is equal to 0, s is equal to 0. So from here it can be derived as fr is directly proportional to s is constant in fe. S is equal to, we already study n synchronous minus nm divided by n synchronous. So putting this here, fr will become n synchronous minus nm divided by n synchronous into fe. As we know, the n synchronous, which is the magnetic field speed, is 120 fe over p. Putting this value here, so fr will become n synchronous minus nm into p divided by 120 fe into fe. So this will become, so fr will become equal to p divided by 120 into n synchronous minus nm. So rotor frequency is directly proportional to the difference between the speed of the magnetic field n synchronous and the speed of the rotor nm, and directly proportional, this is the proportionality constant. So at the end we are going to solve the example number 7.1. In example, it states that a 208 volt 10 horsepower 4 pole 60 Hz Y connected induction motor has a full load slip of 5%. What is the synchronous speed of this motor? Synchronous speed, we already studied that n synchronous is equal to 120 Fe over P. 120 frequency is here 60, and poles are also given here 4. By solving this, it becomes 1800 revolutions per minute. This is the part A. In part B, it's saying what is the rotor speed. Rotor speed Nm, we study Nm is equal to 1 minus S into n synchronous. This is a formula we already derived, 1, and slip is here 5%, so 0.05 into n synchronous, which we already calculated, is 1800. So it is equal to 0.95 into 1800. $17.10. When we solve it, it will become $17.10 revolution per minute. And here, you know, our book is very good. So this is the problem here. It is wrong here. Now part C. Part C states that what is the rotor frequency? Rotor frequency Fr, we calculated that Fr is equal to S of Fe. SR is equal to 0.05 and Fe is equal to 50. We calculate it. Sorry, it is 60 Hz. When we calculate it here, it will become 3 Hz. At the part D, have to calculate the torque induced or torque load is equal to P out divided by Wm. This formula we already study in chapter number 1. Power is 10 horsepower. By converting horsepower into watt, we have to multiply this by 746, and Wm is equal to 1710 revolutions per minute, and converting revolutions into radian, we have to multiply by 2 pi radian, and it is revolution per minute, and converting minutes into second, it is like that, and by solving this, it is equal to 41.7 Newton meter. And further are just the unit conversion, I think you can do it by yourself. So now we are going to finish over this lecture. I hope you will understand. Thank you.